Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today we'll demonstrate an application of power factor correction in three-phase AC systems. This lecture operates under the presumption that the viewer has more than a passing familiarity with three-phase AC circuit analysis of balanced Y-configured loads and power factor correction, as illustrated in the balanced Y configurations and power factor correction lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. For today's exercise, we'll make use of a 180-watt, three-phase AC, Y-configured squirrel cage induction motor intended to operate in a 60 Hz, 120, 208-volt light industrial three-phase AC system. At the rated conditions, this motor will produce 1 Nm of torque and rotate at 1,719 RPM. Let's first examine this motor's electrical performance in the non-power factor corrected scenario. While operating in the rated conditions, the voltage across each winding appears to be 120 volts, and the current through each winding appears to be roughly 1 amp. Load current appears to lag load voltage by a relative 49 degrees. An application of the AC power formula demonstrates that each winding is experiencing 120 volt amperes of apparent power, of which 78.7 watts is directed towards real power, and 90.6 VARs is directed towards a reactive interchange. The Y-configured motor appears to be balanced, and that all three windings are drawing the same amount of current, experiencing the same relative phase shift, and experiencing the same amount of apparent real and reactive power. Total real power is the summation of individual real power figures. Substituting in our given values yields a total real power figure of 236.2 watts. Similarly, total reactive power is the summation of individual reactive power figures. Substituting in our given values yields a total reactive power figure of approximately 271.7 VARs. We can package these as the real and imaginary components of a rectangular number, and then convert it to polar form as 360 volt amperes, which yields our total apparent power figure. You'll note of the 236.2 watts of total real electrical power supplied to this Y-configured motor, 78.7 watts each winding, only 180 watts is converted to usable mechanical power output. This corresponds to an efficiency of 180 over 236.2, or roughly 76%. 56.2 watts of real electrical power not directly converted by this motor into usable mechanical power is considered lost to this system in the form of heat and/or vibration. Additionally, you note that of the 360 volt amperes of total apparent power being supplied to this motor, only 236.2 watts is being directed towards real power, and 271.7 VARs is being directed towards a reactive interchange. This corresponds to a power factor of 0.66. The reactive portion doesn't contribute towards real power transfer. It is, however, essential to the operational principle of a motor that necessitates a rotating magnetic field to function. The fundamental problem with our non-power factor corrected system is that this reactive interchange is occurring over a distance. Perhaps we can power factor correct this system such that the reactive interchange occurs at the point of use. When properly power factor corrected, the motor will still operate as intended. However, line current will be less and will appear to be in phase with supply voltage. Let's see if we can power factor correct this system. You note all the branch impedances of the balanced Y-configured motor are effectively identical, and that they all draw the same amount of current, experience the same relative phase shift, and consume the same amount of apparent real and reactive power. This is extremely convenient. We can effectively treat them as identical independent circuits for the purposes of power factor correction calculation. Given each motor winding appears to consume positive 90.6 VARs of reactive power, we can power factor correct each motor winding by placing a capacitor in parallel with it that supplies an equal and opposite amount of negative 90.6 VARs of reactive power. For a three-phase AC Y-configured load, this would look like another balanced Y configuration floating over the balanced Y configuration of motor windings, only it's composed entirely of power factor correcting capacitors. Each capacitor and each winding would experience a 120 volt differential because they're effectively in parallel with one another. Because each configuration is balanced, we don't really need to join the central connections of the two Y configurations. An algebraic rearrangement of one permutation of the AC power formula suggests the capacitive impedance necessary to supply the required negative 90.6 VARs of reactive power for each winding is 158.9 ohms at an angle of negative 90 degrees. An algebraic rearrangement of the capacitive complex impedance formula when operated at 60 Hz suggests the capacitor has a value of 16.7 microfarads. Unfortunately, the capacitor stored downtown does not have 16.7 microfarad capacitors in stock. However, for every 15.5 microfarad capacitor you buy, you get your choice of a free pit bull, a free handgun, or a free can of 4 Loko. 15.5 microfarads is close enough. I'll take one of each, please. I mean, really, what could go wrong?